Yeah, thank you, and thank you all for attending my talk. Yeah, I today want to convince you all that snapshot fuzzing is awesome, so for that purpose I will first of all introduce snapshot fuzzing, and then I've brought 3 vulnerabilities with me that I found this year. First, like a simple kernel vulnerability that's just here to showcase a basic snapshot fuzzing setup, and then there will be some sort of demo. And then I have 2 more vulnerabilities in the Microsoft Remote Desktop Client. First, an information disclosure, which was found through the address sanitizer-like features, so I will showcase those. And then finally, a remote code execution. And this one's pretty interesting. And we are gone. We're back. It's like it's a cable buggy. What should I do? Okay. Yeah, this one's pretty interesting. It's like a use after free on an event object that's caused by a race condition that then in turn leads into a use after free on a stack variable. So yeah, that's a very inconsistent bug, and so that allows me to really showcase how the determinism and crash debuggability of a snapshot fuzzing setup can really help you understand a very complicated vulnerability. And so snapshot fuzzing, we have a snapshot, so just some memory and some register state of a system, and then we take that snapshot and we throw it into a fuzzer that then is able to execute random inputs and hopefully detect crashes. And your snapshot could, for example, be a WinDBG kernel memory dump, or maybe a VM snapshot, so here someone used VirtualBox to do VM snapshot fuzzing, or maybe even a memory dump you got from like a JTAG interface of an embedded device or something. And then you take that snapshot and you throw it into some sort of execution engine. Most public snapshots fuzzers out there are sort of built on the KVM APIs, but there are also some that use like a hacked up version of QEMU. And you really need some sort of hacked up version, because not only do you need the ability to load your snapshot in your execution engine, but then you also need the ability to quickly reset to the snapshot. So you need some sort of dirty memory tracking or something like that. And then furthermore, you also need the ability to detect crashes. And that might sound trivial, but actually a computer doesn't really know what a snapshot, what a crash is. It might know what an exception is. It might know what a triple fault is, but even in user space, like an exception isn't always a crash. Page faults happen all the time. And on the other hand, like even if you have a blue screen of death, that's not actually a triple fault. And then lastly on the list here I have, if you want to do coverage-driven fuzzing, which you probably want to do, then you also need the ability to collect coverage information in some way. Okay. And if you have your snapshot and your execution engine, then this is sort of the fuzzing loop. So you first of all load your snapshot in your execution engine and then set it up to the exact state that you want to reset to. So for example, be at the start of this function, this like handle packet function, and then each new fuzz case is you write in the fuzz case. So in this case, it would be writing in the buffer, for example, and then you run the function. If you make it to the end of the function, you sort of have a choice. You either reset immediately back to the snapshot, or if you have a packet-driven loop or something, then it might be good to only reset the register state and sort of simulate the next packet coming in. And then if you run the function and it crashes, or there's some hardware access that you don't handle, or it times out, then you also have to reset to the snapshot. Okay. So the system I want to use for this talk is obviously the one I wrote myself. So this is Fuzz, and the idea of it is to be sort of an all-in-one solution. So you have a custom hypervisor in which you can boot Windows 11, and then at any point you can break in like a WinDBG style debugger that then allows you to create snapshots. And the snapshots can then be loaded into the deterministic full system emulator that is specifically designed for snapshot fuzzing. And in particular, there's some sort of framework in place that allows you to implement target-specific code. So this is the code that you write for each new thing that you want to fuzz, and that sort of tells the system what is a crash, what is an input to my system, how do we mutate an input, how do we inject an input, and then how do we run a fuzz case, and so on. Okay, and the first target that I want to look at is the simple kernel vulnerability. And sort of how I got to that is that a couple of years ago, I was watching this talk by Eric Exgard, where he was exploiting a gaggle of Windows privilege escalation vulnerabilities. And I was interested in this talk because he found a bug in the afd.sys driver. And at the time, or slightly before it, I was fuzzing afd.sys. And so, well, at the time I was busy, but then 2 years later, one of my colleagues, so at the beginning of this year, wanted to look at the TDX-TDI interface, and that is sort of what his talk was about. And so I remembered the talk, and I rewatched it, and there were some weird code paths, some unchecked pointers, so I thought, let's fuzz that. And here is more or less the setup he had in the talk. So on Windows, a socket is more or less a handle to the afd.sys driver, and then each of the different socket functions, so sending, receiving, or setting socket options, are calls to NT-device IO control file. This is like the main function that user space uses to communicate to drivers. And there are always some undocumented IO control codes, and one of these, in this case, is the AFD query handles function. And this function allows you, if you've opened your socket in sort of a special way, to get one of these, what I call legacy handles, to the tdx.sys driver. And then you can talk to TCP/IP through tdx.sys instead of through afd.sys. And in this code path, Mr. Exgard found a bunch of bugs. So I thought, let's fuzz NT-device IO control file for this legacy TDX handle. And actually, I want to do this more or less live. So I first of all have a video of how I took the snapshot, and then I have a demo of fuzzing and finding the bug. And so, first of all, I have snapfuzz here, and then I throw in a VHDX, so a virtual hard disk, that I've previously installed Windows 11 on using Hyper-V. And if I do that, then it boots from this virtual hard disk. And you also will be able to see why I decided to make this a demo video, because it takes quite a while. So here I can speed it up. But yeah, after it has been booted, you sort of have the setup that you would expect from a virtual machine. So you can use your mouse and your keyboard. And that allows you to set up the state of the virtual machine to the state in which you then want to take the snapshot. And so for this particular bug, I've prepared this tdx.exe. And what this tdx.exe will do is it will open this legacy TDX handle and then cause a breakpoint in the built-in debugger. So when I continue here, it will execute tdx.exe, and we get a breakpoint in the built-in debugger. And so, well, this is not quite where we wanted to fuzz. What we wanted to fuzz NT-device IO control file. So I put a breakpoint on that function. I continue tdx.exe called NT-device IO control file, and so I can now create a snapshot at NT-device IO control file. Taking a snapshot also takes a couple of seconds because it has to store like 4 gigabytes of data, but then we get our fuzz.snapshot. And this is the state where I want to start the demo from. So I have prepared a command prompt, and on here I have snapfuzz, and I have this fuzz.snapshot. And to show you that this is the precise snapshot that we took in the video, I'm simply gonna take snapfuzz and then recreate the state by putting in fuzz.snapshot. And you can see we have the hacky display here. I can like move around the window. It's a little bit slow. And well, tdx.exe finished, and this is the handle that we want to fuzz. Alright. But now let's not continue from the snapshot, but instead fuzz. And for that, I'm simply going to append --. Then you can see there are a lot of coverage increases. So it's doing coverage guided fuzzing. And after a little bit here, we should find a crash. And this crash is a general protection fault in PCP reference flow. And one of the cool things the system does is each time it finds a crash, it writes out one of these repro files. So I get this file down here that I can then use and throw it back into the system to reproduce the crash. And how this works is, once we found a crash, we save off all of the inputs that led to the crash, and then because the execution engine is entirely deterministic, we can, put in the same inputs again, and if you put the same inputs into a deterministic system, you get the same result, so the same crash. So this is entirely deterministic, so you can do this again and again, and it will always give you the same crash. And then you can also use that to debug by getting into the built-in WinDBG style debugger. So here I'm at anti-device IO control file, I can single step or whatever. And for this particular bug, maybe we would look at the point where it crashes. So this PCP reference flow. So I put a breakpoint there. I continue, and then we are there, and let's see what it does. It tries to dereference RCX plus 268. And if we look at RCX, we can see it's completely busted. There's only a single bit set in the entire address, and that's in the top 4 nibbles, so this isn't even a canonical address. And that is causing the general protection fault. If you try to dereference a non-canonical address, that's a general protection fault. Alright. So much for the demo. And then we can get back to the slides where I have the precise crash trace here. And here I have sort of popped out pseudocode for the top 2 functions. On the top right here, we can see the PCP reference flow function that crashed, and we can also see the access of RCX plus 268. And because this is a reference function, afterwards it's increasing some ref count. Then if we go one layer up, we have the PCP validate and reference flow function, and it takes an input buffer and an input buffer size. And for whatever reason, it decides whether we called it from kernel mode or from user mode based on the input buffer size. But we, for whatever reason, made it into the kernel mode path, and in the kernel mode path, it simply reads out a pointer from the input buffer and then passes it to PCP reference flow. So we can specify an arbitrary pointer in the input buffer, and then in the reference function, it will be incremented. So we have an arbitrary increment vulnerability, and before 24H2, this would have been trivial to exploit. But since then, Microsoft finally removed all of the documented KSLR leaks, at least from medium integrity processes, and so I don't know where anything in kernel mode is. And I simply reported it with this main, so arbitrarily incrementing lead, or whatever. And Microsoft still accepted it as a privilege escalation vulnerability. And probably on most modern hardware, this would still be exploitable because most modern hardware is vulnerable to some hardware vulnerabilities that allow you to leak KSLR. Okay. And then in preparation for this talk, I was actually rewatching the talk by Eric Exgard, and I found this slide. PCP reference flow? Wait, that is my bug. And actually, one slide later, this is the other bug I reported in the same subsystem. So, what's going on here? Well, it turns out, apparently, there was some miscommunication between Mr. Exgard and Microsoft, where he thought 3 of his vulnerabilities were merged into a single CVE, when in reality Microsoft simply didn't patch 2 of them. And they were public for 3 years, and nobody cared. Yeah, not particularly great. Anyway, so much for the simple kernel vulnerability, and now we can move on to the 2 more interesting vulnerabilities in the Microsoft RDP client. And so a couple of words about the remote desktop protocol. I assume most of you know what it is. It sort of allows you to use a remote computer as if you were sitting right in front of it. And what I was fuzzing is the RDP Client. And that is simply a user space application that is using a single socket to do all of its communication. The protocol itself is fairly well documented by Microsoft. So there are all of these different PDF files. You can see some of them on the right there. And the protocol has a couple of channels of communication. There is the basic input-output protocol. That is sort of how the protocol worked initially, but then they introduced static virtual channels and then dynamic virtual channels. And what is important for us sort of is that all of these different channels are viewed as asynchronous, and so they each have their own packet function that we can fuzz. And I, first of all, fuzz the first one on this list, so the CCO on packet receive function. And that function corresponds to the basic output protocol. And it simply has a packet as an argument and then the length of that packet. And also an implicit this pointer because the whole code base is like C++. And alright, I have a little bit of a screenshot here of how I took the snapshot. So I have some sort of custom RDP server that I can connect to with the Microsoft RDP client. And then the server allows me to send a packet that makes it to the on-packet receive function whenever I want to. And then on the outside, I somehow managed to put a breakpoint on the CCO on-packet receive function, caused the breakpoint, and took a snapshot. The corpus is not that interesting, just some packets I dumped, and the mutations also not that interesting. Just some bit flips and randomly growing and shrinking the packets. What is maybe a little bit more interesting is the input injection code. So here I have the target execute input function. And this is one of the functions that is part of the target specific code. So each new target, you would write such a function that sort of tells the system, how do I inject the input and then how do I execute the input. And what it does in this case, it will first of all allocate memory inside of the guest to have space for the new packet. What it means to allocate inside of the guest maybe is a little bit interesting. We'll see that in a couple of slides. But for now, we have some, guest virtual address range reserved afterwards. And then we write in the input buffer into that guest virtual address range. Then we set up the register state to be at the start of this function. And then we also, put in the packet, so the newly allocated thing as the first argument, and then the packet length as the second argument. Finally, we set up returning successfully from the function and execute the function. And after fuzzing with the setup for a while, we get this crash. An out-of-bounds read on a mem copy on a safe session info PDU. And if we look at the arguments to the mem copy, you can see it's trying to copy hex 200 bytes. And if we look at these hex 200 bytes, there are these suspicious looking question marks in there. And so, the questions are sort of, what are these red question marks and what is an out-of-bounds read? And this is more or less the system I want to talk about for this vulnerability. These are the address sanitizer-like features. And so the idea here is to mark the heap metadata of each allocation as being inaccessible. And then, because we are in an emulator, we can check on each read and each write whether the read or write would access one of these inaccessible bytes. And if it would, we immediately report one of these out-of-bounds crashes. This allows you not only detect out-of-bounds heap accesses, but also use after freeze. So on a free, as you can see, we just mark the entire region that's being freed as being inaccessible. And then also double freeze, because if you free inaccessible memory, that's a double free. Okay. And these address sanitizer-like features are powered by extra permissions. Those are sort of the question marks. And then hooks for allocation tracking. And so the idea for extra permissions is that we associate 1 byte of extra permissions to every byte of guest virtual address space. And this works by, when the guest is trying to access some address, we have to perform a page table walk to translate from the guest virtual address to the guest physical address. And just at the same time, we have another page table, the extra permission page table, and we also walk that page table. And if it ends up that we have a extra permission page associated to that guest virtual address, then I will have the code right there. We iterate the entire range that is being accessed and see if any of the extra permission bytes have the inaccessible bit set. And if they do, we immediately report one of these out-of-bounds crashes. For hooks, the idea is also that we are in an emulator, so we have full control. We can execute arbitrary code at any point for any condition that we would like to, and then hooks are simply callbacks that are invoked whenever the guest tries to execute a certain guest virtual address. And one example of one of these hooks would be the drop link immediate function. That would usually be called whenever anything goes wrong in the on-packet receive function. But what it would do, it will shut down the entire connection, meaning that subsequent packets wouldn't do anything anymore. But well, I wanted subsequent packets to do something, and so I hooked the function to simply simulate a return, essentially knocking out the function. Okay, these hooks are then also used for allocation tracking. So on startup, the target-specific code can request allocation tracking by calling a function like register user memory allocation hooks, and it will, first of all, pre-allocate a big region of memory, and it does so by actually calling code inside of the guest. So inside of the guest, then executing a function like allocate virtual memory to reserve a big blob of memory inside of the guest. And it will then register hooks for all of the common allocation functions. So malloc, realloc, calloc, and free, for example. And on a malloc, instead of actually calling malloc inside of the guest then, we simply linearly allocate from this big allocation. Apply the extra permissions, and then return the linearly allocated address, again without ever calling malloc inside of the guest. Similarly, on a free, we don't actually free any memory. We simply mark the entire region that would be freed as inaccessible. But then obviously we can't go on allocating memory forever and ever and never freeing it, but we sort of have a canonical point. Namely, when we reset the entire system back to the snapshot, we also free the extra permission table and the big allocation. And yeah, this subsystem found this crash. So this out-of-bounds read on a mem copy. And actually what it was trying to mem copy is the initial allocation that we made in the target-specific code for the packet. So for whatever reason, this save session info PDU was trying to mem copy from out of bounds of its packet. So why is that? Well, here's sort of the spec for this packet, and there are a couple of different versions and a couple of different types. But the one we are interested in is this logon info version 2. And it has a version, a size, a session ID, a size for the domain, a size for the username, but also, interestingly enough, 558 bytes of padding. And only after this giant amount of padding, there is a variable-sized domain and a variable-sized username. And where's this padding coming from? Well, I think their code probably looks something like I have on the top right here, where they have all of the different versions in a big union. And the version 1 of the structure is pretty big, because it has an inline fixed-sized version of both the domain and the username. But then for version 2, they decided to make both of these variable-sized. So you can see that on the left there. They have sort of a small structure that has a size for the domain and a size for the username. And this differential between these two sizes are these 558 bytes. But this is then also causing the issue, because the code probably looks like the thing on the bottom here, where for the packet size, they use like size of on the member. But size of on the member is only 18 bytes. But when they then access the packet, they probably use like something like packet plus 1, which is implicitly packet plus 576 bytes. So there again, we have this differential, and we can go up to like 558 bytes out of bounds. And we can also choose an arbitrary offset of the end of the packet if we don't use the first mem copy that's copying the domain, but the second mem copy that's copying the username and therefore adding the domain to the end of the packet. Then importantly, this information is also returned to us, namely the username and domain is returned by the client to the server on a reconnect to re-authenticate itself. And so if we do that, it sort of looks like this. I again have a custom RDP server. I connect to that. It sends one of these packets. It sleeps for a bit. And then it's causing a reconnect. The reconnect takes forever, even on localhost for whatever reason. After a little bit, we get some leaked bytes. And these bytes are actually the heap metadata of the next allocation. Okay. So that is sort of the information disclosure. I think the vulnerability is not that interesting, but sort of how we got to it is interesting. And now we get to the more interesting vulnerability, this like remote code execution. And here, maybe first of all, the obvious question, where's my CVE? Why does this have such a shitty title? Well, I was sort of asking myself the same thing. The bug did go through the entire pipeline on MSRC. So we reported it. It got accepted as a remote code execution vulnerability. They gave us our like $5,000 or whatever they give you. And then the vulnerability was fixed. But for whatever reason, they never gave out a CVE. And so I asked, and this is the answer, well, the vulnerable code was introduced in a specific Windows branch, which is not a market Windows version. Hence, no CVE was published. So yeah, what was happening here is that Microsoft always wants you to test your vulnerabilities on the Canary channel, which is like a pre-release version of Windows that already has some bugs fixed. But I didn't want to find bugs that are already fixed, so I fuzzed the Canary channel, but apparently they also introduced bugs on the Canary channel, and so I found a bug that never made it to the normal Windows version. So I guess next time I have to wait until my bug goes live to get that sweet CVE street cred. Okay. And what I was fuzzing is the dynamic virtual channel manager. And the dynamic virtual channel manager is sort of the static channel that implements the dynamic virtual channels. So it gets open, close, and data packets, and then forwards these different packets to plugins, and the plugins then manage each of the individual dynamic virtual channels. What is important for us is that these dynamic virtual channels can be either synchronous or asynchronous, meaning they have their own dedicated thread that handles the packets. And the function I was fuzzing is the onStatic data receive, and the fuzzing setup is fairly similar to the previous one. And for this one, I was fuzzing quite a long time, but eventually I got this crash. And this immediately looked pretty good, because at the very top there, where it says question mark, that is it trying to execute non-executable memory. So if we can take control of that, that's probably code execution. And where are we? Well, we're actually in the startup code for a new thread. So this thread hasn't actually done anything interesting yet. It simply has a thread start argument, and from that thread start argument, it reads out a thread and a thread list. And then it is adding the thread to the thread list, and for that purpose, it's calling thread addref, and that crashes because the vtable is busted. And why is the vtable busted? Well, the thread pointer is busted, and so the contents of the thread start argument are busted. And so, okay, this function hasn't done anything yet. It's still in its startup phase, so probably something did go wrong before this function. So we have to look at where this sort of thread is created. And there I have this pulse system thread alloc init function, and it takes a thread start argument and an init event. It creates a new thread, and then waits until either the thread exits or this init event is signaled. Going one layer up, we can see that this init event is created, and then the thread start argument is allocated on the stack. And so what's happening here? Well, actually, if we look at the thread list once we've crashed, we can see that actually no one is waiting anymore on this call for wait for multiple objects. So that means probably someone erroneously signaled this init event, meaning that both of these functions exited, and then the thread start argument was simply freed because it's simply on the stack. And so the question remains is like, who signaled this init event? I think if you simply had a crash dump, this would be pretty hard to figure out. I wouldn't know how to trace like init events back into the past. But, well, we have a deterministic snapshot fuzzer, so we can restart debugging this crash again and again and again, and all of the values and addresses will be deterministic. And the first thing I want to use this on is this init event handle. And so I did go to the place where this event is created, and the handle value for it is this hex10e4. Now if we restart debugging and get to this again, the handle value will again be hex10e4. Each handle also then has a corresponding entry in the processor's global handle table, and that has some sort of address, and that address will also be deterministic, because everything is. And so we can use that to restart debugging and then set access breakpoints, so both a read and a write breakpoint on that address to see what's happening to this handle. And so then we can see that this handle is first of all allocated as an event in a call to clear channel list. Then it is closed again in a call to clear channel close events. Then it is reallocated as this init event that we saw from the call of thread start. Then it is waited on in the wait for multiple objects, and then it is signaled from some asynchronous channel. So some asynchronous channel woke up and for whatever reason in the end decided to signal this init event. Okay. And, well, these are the functions that we sort of saw in the trace there. First of all, the onStaticDataReceive function is the thing we are fuzzing, and it has some sort of packet, the dinvc caps PDU, on which the whole channel resets. So first of all, it clears the channel list, and then it clears the channel close events. On a call to clear channel list, it iterates all of the channels, allocates close events, sets these close events on the channel, and then calls channel close. And this is sort of the interesting part because, well, if it's a synchronous channel, this means that the on-close callback, there's an on-close callback which happens immediately. But if this is an asynchronous channel, then the on-close callback will be queued on the dedicated thread of that channel. But this then causes the issue because on the call to clear channel close events, this isn't waiting for all of the different closes events. It simply closes all of the events. So that can mean that the on-close callback on the asynchronous channel happens too late, meaning that it then signals the close event later than it was freed. So this is the race condition that leads into a use after free on an event object. So how do we exploit this? Well, we first of all allocate one of these asynchronous channels, and then we also allocate a bunch of synchronous channels. We reset the dynamic virtual channel manager. This will cause it to allocate close events, then queue a on-close callback, and then close all the close events again. And so once the on-close callback is queued, we are sort of in the race. And during that time frame, we first of all allocate a new asynchronous channel because the asynchronous channel will then also spawn a thread. And the thread sets up a bunch of different handles. Handles on Windows are allocated with a last in, first out free list. That means the synchronous channels that we allocated in the very start there, the close event handles for those will get allocated first. And so that allows us, by specifying the amount of synchronous channels we allocate, that allows us to line up the close event with the init event. And so then when the on-close callback happens, it will erroneously signal this init event, meaning that the wait for multiple objects will return to early and we will free the thread start argument. And because that's simply on the stack, we can then send another packet to corrupt the stack or reuse the stack and corrupt the thread start argument. Okay, and so if we do that, I have a custom RDP server again. I connect to it, does the RDP handshake, waits for a bit, then sends these create events, sleeps again, and then, well, nothing happens. Well, why not? After much more debugging, I figured out that the thread order is different between the two versions. So between the time I have the original and then the time I was trying to repro it. They both wait on this init event. And then in both cases, the init event gets erroneously signaled from this onClose callback. But then for whatever reason, when I try to repro the crash, the new thread starts up first before the wait for multiple objects exits. But in the original, the wait for multiple object exits first, meaning that the thread start argument gets freed and the new thread that starts up gets, crashes. And so for whatever reason, the threads are scheduled in a different order. On Windows, scheduling is priority based and round robin at the highest priority. So probably this has something to do with thread priorities. And so I wrote a little thing that dumps out all of the different thread priorities. And so here they are at the start for wait for multiple objects. So when it's starting to wait on the init event. And then we can see when I try to repro the crash, all of the different threads have thread priority 10. Whereas in the original, the wait for multiple objects has thread priority 9, whereas the new thread only has thread priority 8. So that explains why the wait for multiple object exits first, and then the new thread starts up in the original, but when they all have the same thread priorities, so in the repro, well, it's based on round robin, so yeah. And why is this happening? Well, priority boosts. So on Windows, a normal thread has normal priority class of 8. But then whenever a wait condition is satisfied, so a thread was waiting on an event and that event got signaled, then the thread gets a small priority boost to priority class 9. But there's also a thing that when a process has a foreground window, all of the different threads get a foreground boost to thread priority 10. And importantly, threads that already have a foreground boost don't receive these priority boosts anymore for whatever reason. And so these are exactly the values that we saw, right? 10 and 9 and 8. So probably what was happening is that, well, the process had foreground, and so all of the different threads had priority level 10. So if we first of all minimize the window before attacking, it should work. And so here I have the exact same executable. I connect to it, but this time I minimize the window. Then we can see we have to look in the bottom right here, sort of, and we can see it crashes. Boom. All right, and now we have an information leak, and we also have the ability to execute an arbitrary address. So let's exploit it, right? Well, actually I did not bother. I simply shipped these two bugs exactly as if you've seen them to Microsoft. One just leaking some heap metadata, and the other one crashing in a way that looks really good. And Microsoft accepted them both, so good on them, I guess. And yeah, this is sort of the end of the talk. And if you found it interesting and you see me around the conference, please talk to me. I would love to get in touch. Also, Fuzz is finally open source as of today. I pressed the button this morning, so you can find it on the Fraunhofer FKE CAND GitHub page or by scanning this QR code. And with that, I'm ready for questions, if there are any.
Any questions? Oh, hey there. So I wanted to ask about your, how do you call them, extra memory permissions.
Yeah.
So they're implemented in your hypervisor?
No, they're implemented in the full system deterministic debugger.
Does this incur any kind of perf issue?
Yeah.
Yeah. Did you try to use something in the OS itself, some patches, page heaps, or whatever? Did that maybe speed it up a bit, or was that kind of useless?
I did, I initially tried to patch up quite a lot to even make it work, but yeah, I mean, then I implemented a bunch of stuff. It kind of depends on what you're fuzzing, how the performance is very much. Yeah, so not particularly any.
Well, great project regardless. Thank you.
Yeah, thank you for the talk. do you have any idea or feedback from Microsoft why they are not sort of doing this themselves? So fuzzing is not that new. There are plenty of fuzzers out there. Shouldn't they be able to find these kinds of bugs themselves?
I mean, maybe. I don't have feedback from Microsoft. No, I haven't really talked to Microsoft, other than like with some Microsoft employee in the MSRC forums. No, I don't know. Obviously, they probably should do some fuzzing. Maybe they do. I don't know. There are some fuzzing things for drivers. If you want to ship a driver and have it signed by Microsoft, then you have to go through some sort of fuzz testing for something, but I don't know if it really works that well. Yeah.
Thank you.
Any other questions?
All right, then thank you, Pascal, for making it open source and sharing it to the community.